Welcome back, Organickers. This is John Hansen, and in this short video I'm going to just give you a quick overview of Proton NMR, quick review, so that you're ready to go for class tomorrow. So what you might want to do is pull up the Moodle site, and I've put up a file, this introductory H-NMR, which I'm going to be describing, and you might want to go ahead and pause the video and print that out so that you can annotate it as we go along. So here's the introductory NMR. It's a fairly simple one. If you had me last semester, we used this as a sort of quick introduction. It's this compound shown here, this trichloroethane. So to start our discussion of proton or hydrogen NMR, it's important to note that what we see in the NMR is due to hydrogens in the molecule. So if you had a molecule with no hydrogens, you'd have no signals in your NMR. If we look at the NMR signal, you'll see that this is a baseline coming along here, and then we have little peaks coming up at various points in the spectrum. So unlike IR, where the peaks go down, in NMR the peaks are typically presented going up. Each of the hydrogens in the molecule will show a signal in the proton NMR. There's lots of different information we can get in proton NMR, which makes it a lot more powerful than the IR spectrum, and we're going to go through some of those right now. The first thing to note is the axis. The axis is related to the frequency of the absorption, but it's given this funny unit, parts per million. That parts per million is due to the fact that we're referencing relative to some standard signal. And so at 0 parts per million, and by the way, parts per million is often sometimes, this axis is sometimes referred to as chemical shift. So this signal at 0 parts per million is due to tetramethylsilane, which is the standard that's normally used for NMR. So I'm going to go ahead and put a little arrow. You might want to annotate this. So tetramethylsilane is often given the shorthand TMS. So here's our TMS signal, and so most proton NMRs will have a signal there unless people didn't put the TMS in for their standard. It's a nice thing to use because it's very volatile, so when you evaporate off your sample it goes away again. So if you want to recover your sample, it won't be contaminated with the TMS. Now you'll notice we also have another small signal down here. That's also a function of the solvent that we're using. So if we used a solvent that had protons in it, that would give a very, very big signal. And so we typically use deuterated solvents in proton NMR, and the most common by far is deuterochloroform. Deuterium, as you know, is the heavy isotope of hydrogen, so you could have a solvent where you replace the hydrogens with deuteriums, and then you wouldn't have that showing up in your NMR spectrum. The most common one is deuterochloroform, CdCl3. And when you buy the deuterated solvents, they're not 100% deuterium, so there's a little residual chloroform in there. So this signal that we're seeing with a chemical shift of about 7.26 ppm is in fact the residual chloroform, CHCl3, that's in our sample. So you'll almost always see a little peak like that in a typical proton NMR if it's been acquired in chloroform or deuterochloroform, which is by far the most common. The other two peaks are actually due to our sample. So we can see we have a peak here at a chemical shift slightly below 4 ppm and another one that's slightly below 6 ppm. Now when you look at a proton NMR, you can get a lot of information by first just looking at how many peaks you have. So here we have 2 different peaks. And you might wonder, well, why do we only have 2 different peaks when there are 3 different protons? Well, that's because these 2 protons are equivalent to each other, so they have the same chemical shift and appear in the same place, whereas this proton, which is on a carbon with 2 chlorines, is in a different place. So that's going to cause it to be in a different environment and to have a different chemical shift. The differences in chemical shift are in some senses analogous to the differences in the absorption frequency in the IR, and they give you information about the environment of the proton. And we can often assign the hydrogens in the molecule by looking at where they come. So for example, these that come at about 4 ppm are the hydrogens that are next to 1 chlorine. The hydrogen that's next to 2 chlorines gets shifted up further. This is very characteristic of electronegative atoms, is that they tend to cause things to shift to higher frequency. So one of the first things that you need to do when you're looking at an NMR, or as you're starting to learn NMR, is to think about the chemical shift and what that tells you about the molecule. And we'll be spending most of the time tomorrow in class doing that, and I'll say a little bit more about that in a moment. Another piece of information that can be very helpful in interpret the NMR is shown with these little lines sort of coming up and leveling out here. This is called an integration, and what it's telling us is the area under these peaks. And that area, turns out, is directly related to the number of hydrogens. This is in contrast to the situation in IR where, for example, some stretches absorb more than others because they have larger dipole moments. In proton NMR, we have sort of a direct relationship between the number of protons and the strength of the signal. And so from the integration, we can tell the relative number of protons. Now when you look at an integration, what you're really looking at here is if you sort of started at this line and then measured with a ruler all the way up to that line and compared it to the distance to go from there up to there, that would be the relative number of hydrogens. So let me use a little box to do that. I don't really have a different way to display this. So I'll kind of put a little box here and I'll move it. And what I want here is so that the top of the box is kind of even there and the bottom of the box kind of goes with that one. And I'm going to try to do the same thing with this guy, just as a way to kind of have us to be able to see the height of these things. So normally what you would do is get your ruler and measure the distance from there to there and the distance from there to there, and you can pretty easily tell that this one is twice as high as that one, and that means that there's twice as much area in these signals, which means there's twice as many protons, so you can immediately tell that that signal is due to those two protons and that other signal is due to that proton. And so the integration can be very useful. In a lot of the problems that we'll have, we'll be giving you a formula so you'll know how many total hydrogens there are, and from the integration you'll be able to assign each peak to a certain number of hydrogens. So that can be very useful. Okay, I'm going to go ahead and remove those integration signs there. So we have integration and the chemical shift, and then one last piece of information that's really valuable is the splitting pattern. So you can see here that we have 3 peaks, 1, 2, 3. In that signal, that's referred to as a triplet. In this signal, we have 1, 2 peaks, that's referred to as a doublet. Sometimes you see things like this, which is a single peak, we call those a singlet, and you can have even more complex spectrum, splitting patterns as they're called. Those splitting patterns are really valuable because they tell us something about the number of neighbors. So if we have these hydrogens equivalent to each other, it turns out that they don't split each other, but they are split by non-equivalent neighbors. So, and what do we mean by a neighbor? Typically that's something that's 2 or 3 bonds away. So if I look at this hydrogen, 1, so there's 1 bond, 2 bond, 3 bonds from that neighbor. So it will typically be split by it. And each neighbor typically splits things into 2 peaks. So these 2 hydrogens are split by this hydrogen into 2 peaks, so we get a doublet. And remember, they don't split each other because they're equivalent. If we come over to this hydrogen, it gets split by 2 neighbors now, this one and this one. And that leads to this triplet pattern. So what you can see is we can tell the number of neighbors by the type of pattern. If the hydrogen has no neighbors, then it'll be a singlet. 1 neighbor, it's a doublet. 2 neighbors, a triplet, etc. We'll talk more about that on Friday. I'm not going to go into too much detail on that right now. What we're going to be doing tomorrow is really focusing on chemical shift. So I want to show you a couple resources that you should look at and bring to class. You actually got these in a handout yesterday, so you don't need to print them out. But the one was this overview of chemical shifts in H-NMR, and so I'll bring that up. So this is again a place where I've tried to condense down in one document the information I'd like you to know about chemical shifts. And just like we had ranges in the IR that gave us information about whether we had a carbonyl or a C double bond C, we can get similar information out of the proton NMR. So for example, if we just had an alkyl chain, that typically is going to come somewhere down around 1 parts per million. I mentioned earlier with the chlorines that electronegative atoms tend to cause things to shift up higher. So sure enough, here's our methyl group with a chloride is coming at 3.1, whereas a methyl group with a fluoride comes up even higher at 4.3 ppm. By the way, these chemical shift effects are additive, so if I had 2 chlorines on that carbon, this would come up more like 5.2 parts per million. There are some very nice distinctive regions. Probably the most common that we can see right away from an NMR is the aromatic region around 7 ppm. There's also alkene regions that come slightly higher. Much higher than that is an aldehyde, and aldehydes are very easy to pick out in the NMR because there's not typically things that come up around 10 parts per million except an aldehyde proton. And finally, even higher, we can sometimes see a carboxylic acid proton up around 11 to 13, and it's somewhat variable, but up there, and usually very broad signals, just like we saw broad signals in the IR of hydrogen bonded molecules. So what you'll want to do is probably make flashcards with these different ranges on them so you get used to looking at them and knowing what sorts of things come in those areas. Finally, for preparing for tomorrow, what I'd recommend you do is you look at this NMR primer document. I've got that displayed right here, and work through about the first 4 sections. That's about the first 6 pages. Read through them, get the information. It talks about integration, talks about chemical shift, talks about equivalency. Remember I said hydrogens that were equivalent didn't split each other, so there's a nice discussion of that. And then there's some nice problems for you to work to see if you're kind of getting those concepts right. So there's chemical shift being discussed there. There's integration. And if you work yourself all the way down through problem 6, that would put you in good shape for class tomorrow. As I mentioned, tomorrow we'll be focusing on chemical shift, and then on Friday we'll focus on splitting and multiplicity. Okay, see you tomorrow.